Hello. In the previous videos we introduced the Rankine cycle, the preheater, and we talked mainly about water power systems. In this video we're going to talk about gas power systems. So instead of having water as our working fluid, we're going to have air. So the most typical example is the air standard Brayton cycle, in which we have a compressor which takes air from the environment, compresses it, then we have a combustor, then the hot air goes into a turbine, the turbine generates work, some of that work is used to run the compressor, and then the gases are exhausted into the atmosphere. To close this cycle, we can assume an imaginary heat exchanger over here, which would cool our exhaust gases and then would be used again for the same cycle. So going through each component individually, we start with the turbine. The turbine creates power turbine over mass flow rate, which equals H3 minus H4. Okay. Going at the combustor, we offer heat at a rate of Q dot in over mass flow rate equals H3 minus H2. Going to the compressor, we need to offer work WC dot over M dot equals H2 minus H1, and at the heat exchanger here we reject heat at a rate of Q dot out over M dot equals H4 minus H1. We can calculate the efficiency of the plant as N equal W turbine minus W dot compressor divided by the heat addition. And exactly as in the Rankine cycle, this will equal H3 minus H4 minus H2 minus H1 divided by H3 minus H2. And on the TS diagram, the compression is considered isentropic, the heat addition isobaric, the expansion isentropic again, and this heat rejection isobaric again. So it's very similar to the Rankine cycle. So on the TS diagram we can see the heat offered to the cycle, the Q in, which is the area under the curve from 2 to 3, so this red area over here, and the heat rejected is from 4 to 1, so this blue area over here. Likewise, if we plot the PV diagram over here, specific volume pressure diagram, we said that heat addition 2-3 is happening under constant pressure. 2 to 3, The same with the heat rejection 4 to 1. One to 2 compression is isentropic, and the same with the expansion 3 to 4. So as a result, this green area is the work we need to offer to the compressor, and this red area is the work we get from the turbine. So the difference in purple is the useful work we get from every cycle. We define the back work ratio as the work we need to offer to the compressor divided by the work we get from the turbine. So the green area divided by the red area, or from the enthalpies, this equals H2 minus H1 over H3 minus H4. For gas turbines, the back work ratios are of the order of 20 to 80%, and this is a lot higher than in vapor power plants, which is of the order of 1 to 2%. So, keeping these two graphs in mind, let's assume that we run our compressor to higher pressure, so we increase the pressure at the exit of the compressor from 2 to 2 prime. So we compress from 1 to 2 prime, we follow the isobaric line on the TS diagram from 2 to 3 prime. And then we expand isentropically up to 0.4, then we reject heat at constant pressure 4 to 1, and we continue the cycle. So immediately we see that the work we get from every cycle has increased a lot. So immediately we have all this purple area instead of the previous small region over here. But this comes at a cost, and the cost is that our 0.3 prime has a much higher temperature than 0.3 over here. So this means that our turbine is going to see a lot higher temperatures, and the metals here will not be very happy. Actually, the ratio of P2 over P1, we call it pressure ratio, and we know that as we increase the pressure ratio, the efficiency of our Brayton cycle increases as well. So it follows a curve like this, where the horizontal axis is the pressure ratio, P2 over P1, and the vertical axis is the thermal efficiency. Now, let's look at another case. Let's assume that we have the same turbine. Okay, so the turbine has a maximum temperature that it can withstand at the inlet, so at 0.3. So now we cap our temperature 3. Okay, so we cannot exceed this temperature 3, otherwise we'll damage our plant. So let's increase again our pressure ratio. So let's increase again pressure 2 from P2 to as high as we can go, P2 prime. Okay. Then follow the isobaric line up to temperature 3 and then expand isentropically up to pressure 4. So now let's see what we've done here. So earlier the work produced was this green area, and for it we had to pay all this red heat. Let's make it orange. All this orange heat down under the curve 2 to 3. Okay. Now with the higher compression ratio, going to 2 prime, the work we get per cycle is this black area. So it is smaller than the green for sure, but the amount of heat we paid in blue is less than before. So what we achieved by increasing the compression, the pressure ratio, is that we increased our thermal efficiency. But what we need to make clear is that the net work produced per mass flow for this cycle is smaller than for this. So I had W net over m dot decreased. Exactly as we did in the Rankine cycle, we could make use of some of the heat we reject here. So use a regenerator or a heat exchanger. So we can take our hot exhaust gases from 4 and pass them through a heat exchanger to preheat the gases here and then exhaust the gases. So this will be point X and this point Y, exactly as we did in the previous video. But another application of the gas power systems, more interesting than the vapor power system, is the use of a second combustor, a heat combustor. So after our initial compression of 1 to 2 and our initial combustion 2 to 3, we can add more heat in a second combustor from 4 to 5 and then have another turbine generating more work. So we offer heat here and we offer heat here. So let's look at this process on the TS diagram. So we have the compression 1 to 2, the first isobaric heat